Hello friends, let's continue our discussion on understanding the behavior of a material when you impose a mechanical condition on it. Now if you could recollect, we began our understanding by focusing on rather a one-dimensional system. So we considered a system with length L, and then we imposed a load, a tensile load rather P, and we wanted to understand how the longitudinal dimension of this material varied. For that, we want to quantify the mechanical condition in such a way that it was independent of the dimension of the specimen. So therefore we normalized the mechanical condition with respect to the area of cross section of the material, and thereby we ended up with a description for what we now call it as stress. So we have now a description of stress, which is nothing but the ratio of load that is acting upon a material and the per unit area of the cross section of the material. And then subsequently we introduce what we refer now to as strain, which is nothing but the change in the longitudinal dimension of the material with respect to its original dimension. And now we realized that these descriptions were rather confined and were rather restricted to the one-dimensional system. So we started to build up on this understanding, and we extended this to rather a two-dimensional system, or we focused on the change in the dimension under the similar condition of tensile loading, or change in the shape of the material under the condition of similar tensile loading. We included the other dimension of the material. We wanted to see how the lateral dimension of the material changed when you imposed a tensile loading to the material, meaning instead of focusing on the just longitudinal change in the dimension of the material, we began by considering a two-dimensional setup, and we saw that with the increase in the length along the longitudinal direction, we realized that there was a decrease in the width of the material or the dimension along the lateral direction. So in order to quantify that with respect to the change in the longitudinal direction, we introduced what we refer to as Poisson's ratio, and this was nothing but the ratio of the lateral strain with respect to the longitudinal strain, with a negative symbol here representing the convention that we need to include when you consider a compression loading condition. Now since the lateral strain is nothing but the decrease in the dimension of the material along the lateral direction, in materials or particularly in metals and alloys, this negative sign that is given from the convention will turn into positive, since the lateral strain is nothing but a decrease in the dimension of the material along the lateral direction. So therefore the negative sign that we implicitly have in front of the ratio of lateral and the longitudinal strain, this negative sign vanishes, and every material that exhibits shrinkage in the lateral direction when there is an increase in the dimensions along the longitudinal direction, we refer to them as a material that has a positive Poisson's ratio. Now we began with a one dimension. We considered a change in the lateral dimension when there is a change in the longitudinal dimension, and then we built on that. We considered a two-dimensional system. Wherein instead of just a longitudinal load, we assumed there was also a load in this direction as well, in the orthogonal direction or the perpendicular direction as well. So we consider such a system. We considered load in both y and the x axis. So we considered load both x and the y axis, and we tried to arrive at a relation between or rather we tried to calculate the overall strain along the y direction because of the longitudinal load, that is py, and also because of the lateral load px, because rather the lateral load px contributes to the longitudinal expansion through the Poisson's ratio, and we tried to calculate the overall strain that a material experiences under a condition like this, and we did that by using Poisson's ratio and our initial relation that the stress and strain, that is this ratio, would lead to the Young's modulus. So with combination of these two relations, like using Poisson's ratio and our definition of the Young's modulus, we were able to calculate the overall strain that a material experiences in a in a given direction when there is a load that is also acting on a perpendicular direction. So in this case, we were able to calculate the epsilon y as epsilon y due to the load in the y direction, and also epsilon y due to the load in the x direction. If you could recollect, we did this in the previous we did this in the previous lecture or a lecture before that. Now we also built on that, and we considered a three-dimensional system where we had load acting on all the three dimensions, all the three orthogonal dimensions, and we calculated similar strain in all the three dimensions. So we had load acting in all the three dimensions, and we calculated the overall strain that a material experiences. So if you say this x and y and we calculated the overall strain a material experiences in each of these directions, and we were able to arrive at what we now refer to as the bulk modulus. Now we began with Young's modulus, and we built on that, and we arrived at what we now call as Poisson's ratio. And using our understanding of these two, we tried to address a problem of two-dimensional deformation when there is load acting on both the directions, and based on that understanding we arrived at what we call as the bulk modulus. Now in this lecture we will try to understand something, a new form of a deformation. So we have so far seen elongation, we have so far seen compression, and all these have to do with a tensile loading or a compressive loading, and so these different types of changes are often referred to as deformations. And in this lecture we will try to look into a different form of mechanical loading and the response of the material to that loading. Now when we talked about tensile loading, we showed that the loading directions are something like this. This would be for the tensile loading, and for the compression loading it would be something like this. Now one way we could think about it is we can ensure that the material is held at one end of the material is held at a static point, and the load is applied at the other end. So depending on the direction of the load, the stress experienced by the material can be tensile or compressive. So instead of applying load in both the ends of the material, we can hold or fix one end of the material and apply the load at the other end. So this would mean that depending on the direction of the load, we will be able to apply similar kind of we will be able to impose similar kind of mechanical condition as we have seen here. When the two ends were free, we will be able to impose similar conditions even when one end is fixed. Now, so these help us to understand how tensile loading and compression loading is applied. Now if you could go back to our first lecture, we had a similar setup, and if it is also possible for us in this setup to introduce torsional loading if you could turn the material. Now supposing, let's just say that instead of fixing your material here, we fix our material along the longitudinal direction. So instead of fixing your material at one of the longitudinal lengths, we are fixing our material in the longitudinal sides or the longitudinal axis. So you end up with something like this. So here this end of your material is fixed, and now what you are doing is you are applying a load in this direction. You are applying the same amount of load in this direction. Now what happens is that the material deforms in a way that we have not seen so far. What happens is the material, this initial material which is fixed here, now it deforms in this manner. So let me get fancy and use a new color. So it deforms in this manner. So you apply a load here P, and the material which was a regular rectangular shape earlier, it has deformed, or it has undergone some sort of a shape change, and it has now assumed a form that is like this, that is shown in the red. Now this is what we refer to as is the shear deformation or shear distortion. So what we have seen here is shear deformation. So a material, instead of expanding or compressing, what happens is that it has sheared. So if you have something like, I don't know, like this, so it has sheared, and you have now, instead of a regular rectangular shape, assume this to be a regular rectangular shape, you now have a shape something like this. Now this is what we call as shear deformation. Now let us characterize this shear deformation. So based on our understanding of the tensile, what happens during a tensile and compression loading, let us try to characterize this shear deformation. So first thing you could observe is, when you try to say pull this initial material using tensile loading, when you try to stretch it, even though the material elongates, what happens is that the orthogonality between the length and the breadth, that is the perpendicular relation between the length and the breadth, will not change during tensile loading or even compressive loading. When you compress it or when you stretch it, the perpendicular nature or the orthogonality between the length and the breadth will not change. However, in shear loading, this angle or this perpendicular nature, this 90 degree is lost. Now what you have is some sort of an obtuse angle. This is one of the characteristic feature of the shear deformation. The other change is, as you can see here, even in this graph, supposing if let me try to build this for you. So supposing if I try to slice this, or if I try to make linear or horizontal elements like something like this, if I consider some horizontal elements within the sample something like this, and the bottom of the sample here is being fixed. Now if I consider the horizontal elements, say we have considered the overall setup, we have partitioned it into several horizontal elements, and these horizontal elements, say A1, the A1, this horizontal element, will either increase in size or decrease in size during compression or during tensile or compressive loading. So when you have a specimen and you mark some horizontal elements on them, when you give a tensile loading, the size or the length of this horizontal element will increase. If you shrink or compress, impose a compressive loading, the size of this horizontal element will decrease. Now in case of the shear stress or in case of the shear deformation, when your material deforms like this, what happens is that the size of the horizontal elements remains unchanged. So when you consider an horizontal element in a material and you impose tensile or compression loading, the size of this horizontal element changes, but in case of shear loading, the size of the horizontal element will not change. Now this is in the case of the horizontal elements. Now if you consider rather a vertical element, like instead of the horizontal, if you consider a system and if you could decompose that system or you could partition that system into vertical elements. Now the distance between the vertical elements changes when you impose a tensile or compression loading. If you impose a tensile loading, the distance between these elements increases. If you impose a compressive loading, the distance between those elements decreases. But what happens is that when you impose the shear condition, you will be able to see that the distance between these two will not change, but rather they continue to remain parallel, but now they are inclined. When the shear loading is imposed, now they are inclined. So these are two additional features, or rather three additional features to characterize the shear strain or the shear deformation. So one is the length and breadth, they have lost their orthogonality. The other is the vertical elements, which changes during tensile and compressive loading do not change during shear deformation, or rather the horizontal element, the size of it changes during compression or tensile loading, will not change during shear deformation. The vertical elements which remain perpendicular and which are parallel in nature, and the distance between them which changes during tensile and compressive loading will not change during the shear deformation, but rather they get tilted. Now the other way to characterize shear deformation is that we saw that in case of tensile and compression loading, there is a lateral strain, and this lateral strain led to what our understanding of Poisson's ratio. But in case of shear deformation, there is no lateral strain. So this is one way to characterize, or this is one of the properties or characteristic features of the shear deformation, is that there is no lateral strain involved. There is no change in the dimension along the lateral direction if you impose a load along the longitudinal direction. So these are some of the ways you can characterize the or you can differentiate a shear deformation from the or from that of the deformation that you observe during tensile or compressive loading. Now let us try to quantify the mechanical conditions that is involved during the shear deformation. So we have done that with respect to the tensile and compression loading. We will try to do the same for the shear loading condition. We will try to quantify the mechanical condition for the shear deformations that we see. So in case of compression and tensile loading, we saw, or we quantified the mechanical condition as stress, which is the ratio of load with respect to the cross-sectional area of the material. Now we saw that this load can be expressed as something like this, meaning the stress is nothing but a resistive force that a material offers for a given unit area. So this is how we introduced ourselves to the stress and this is how we related the stress and the load. Now let us try to come up with an expression for the load, or let us try to come up with a way to quantify the shear load that causes a deformation that we have characterized moments before. So now when we consider a setup like this, and there is a load acting on it, say P. Now the material has sheared in this way, and there are two areas wherein the load acts. So there are two areas, let's just assume this is area 1 and this is area 2. Now which area would correspond or would help us quantify this shear stress? So we need to have one area that would help us quantify the stress. So in case of our description here, we saw that it is dependent on cross-section area. So if you go by that definition, if you go or impose the same definition or consider the same definition for the shear stress as well. So if you denote shear stress as something like that, it would mean the expression for the shear stress would be P by A1. If you consider a system similar to the tensile loading, wherein the stress is defined as the ratio of the load and the cross-sectional area, then if you consider, or if you try to use or adapt a similar definition for the shear loading, then the expression would be something like load per area A1. However, there is a sort of an inaccuracy here. The thing is, when we talked about the cross-sectional area, or when we introduced a cross-sectional area, if you could recollect, we meant that the cross-sectional area offers a resistance, and this resistance increases with the cross-sectional area, and this is what we showed by this expression, that the stress is nothing but the resistance imposed by the material, and this resistance was proportional to the area. Now when you impose a load in this direction and the material slides in this direction, is this area creating the resistance or this area creating the resistance? You have to think about that. When I impose a load in this direction, and when my material, instead of shrinking, it deforms in this direction, you have to think which is the area that is giving me the resistance, and you have to include that area. So if you go by that definition, then this is rather inaccurate. The exact expression for the shear stress would then be P by A2. So you have to understand that the area that gives you the resistance, the area that prevents the deformation of the material, should be the area that has to be included here. not the area where the load is applied or where the load comes into contact with the material, not that area, but the area which gives you the, or which offers the resistance, or the area or the resistance is proportional to a particular area, and this area is what you should consider when you calculate the stress, and by that definition the shear stress is expressed as P by A2, that is this area, the area that is parallel to the load. Now if you want to distinguish, when you consider a simple system with cross sectional area A and you applied a tensile load, then your stress was the ratio of load and A1, and this area was perpendicular. So this area A, rather this area A in case of tensile loading was perpendicular to the load P. Now when you want to consider a tensile or rather a shear deformation, wherein the material deforms in this manner, undergoes a shear deformation, then the shear stress that causes the deformation would be expressed by, let this area be A2, is expressed by P by A2, and in this case of shear loading, the load and the area are parallel to each other. In case of tensile loading, the area that offers the resistance is perpendicular to the loading. In case of shear loading, the area that offers the resistance, that is A2, is parallel to the loading or the shear loading. So this is how we arrive at the expression for, this is the normal stress, or let's just say this is the tensile stress, and this here is the shear stress. So now we have shown how to quantify the shear loading condition or the mechanical condition that causes the shear deformation. Now let us see how one can define the response of a material to such a shear loading conditions. So for that, instead of considering a rectangular sample, let us assume some sort of sample that is close to a square, because that will help us to describe the response or the strain that the material experiences during this shear loading. So we will have a material something like this, which is fixed along the longitudinal axis, and now we are applying a load P, and then the material deforms in this manner. So now the deformation that the material experiences, so what happens is there is not much change in the dimension of the material. The only dimension that changes is this dimension here, that is, if you say this as L, it has changed to L1, but even that is not much change. The greater or the visible change in the material happens here, wherein the corner of the material has moved from point A to point A1. So the strain, which we often relate to the macroscopic change in the material, is now not the change in the dimensions of the material. The dimensions of the material are more or less the same. The macroscopic change that happens in the material, which we often refer to as the strain. The macroscopic change that we often refer to as the response of a material to a mechanical condition. This change is clearly visible in the shift of the corners. So A, which was originally here, the corner which was originally here, because of the shear load, it has moved to a distance here. So this is the deformation or the change that happens when you impose a shear loading. Now when you want to quantify this in relation to the original dimension of the material, then you do it by this. So A1 with respect to this length, that is here to here, so this length, which we call as L, so A1 by L. So if we call this as a shear or a change in the position of the corner from A to A1, and with respect to the length here L, so this has also undergone a change. So by taking the ratio of this shift in the corner with respect to the original length, you arrive at what we now call as the shear strain. And this shear strain, or let us use a new symbol for it, delta, this shear strain is the ratio of the shift in the positions of the corner with respect to the original length. If we call this shift in the position as say dl, like what we have considered in the actual strain case, then this delta here, that is the shear strain, is dl by L, and this dl is not L0 minus L, so it's not just the change in the longitudinal length, but this dl is the shift in the corner of a regular square like sample. So it has moved from point A to point A1, and this shift we call it as dl, and we normalize it with respect to the initial length of the material, and this ratio will give us the shear strain. So what we now have is a shear strain of this description and a shear stress of this form tau, which is nothing but the ratio of load and area. But you should remember that in case of shear stress, the load and the area are parallel to each other. So we have now a definition for, or a description for, the shear strain and the shear stress. Now in the elastic region, like the other stress and strain we have seen earlier, this shear stress is proportional to the shear strain, and the constant that relates these two are referred to as the shear modulus, and this is represented by G. So like the regular stress and strain, which are in the elastic region, which are parallel, there is a shear stress and the shear strain, and these are also proportional to each other and linearly proportional to each other in the elastic region, and we use the constant of proportionality, that is the shear modulus, in order to relate the shear stress and shear strain. So let us build on our understanding. Let us build on this understanding in order to see how we can quantify, or how we can define, or how we can qualify the shear modulus that we have, and see how the shear modulus will relate to the different change in the shape that we see during the shear stress. So when you apply shear stress to a material, there is a change in the there is a change in the shape of the material. It is unlike the change in the dimension. In case of the shear loading, there is a change in the shape of the material. How this modulus here helps us to quantify this particular change in shape of the material, we will see in the subsequent class, because to bring that in this lecture will be will make this lecture quite a lengthy one. So let us build on this understanding of what a shear strain is and what a shear stress is. We will build on this understanding, and we will try to see how the shear modulus helps us to understand the change in the rather the shape of the material, and how it helps us to quantify the change in the material when you apply a shear stress, as we have seen here. So with this, I would like to say, I would like to end this part 1 of this lecture, wherein we have just introduced ourselves to shear stress and shear strain. Let's build on that in the subsequent lecture. So let's see ourselves in the part 2. Thank you.